Welcome back, and I do hope you and your family are keeping well. So, what I wanted to look at today was energy, and particularly energy resources. And we're going to look at a couple of things. But if you think about it, you've got the ability to kind of do things, to run around and to play sport, etc. So there must be something in you that allows you to do those sort of things, because you always talk about not having energy when you feel tired. But the bit I really want to look at today specifically is the other things around you and in your house. So you've got things that move fast, that rotate, that make a noise, that heat up, things like, washing machines. You can plug your phone in and charge it up. Now, where's that energy coming from? Where's the energy coming from that makes those things work? So what we're going to look at today is energy resources. But first, a little bit of a story to introduce this. And I kind of changed the story slightly to make it run a little bit better. So if you look things up on Wikipedia, it won't quite say what I'm saying. But I'm trying to give a good example of what this chap got up to. So there was a guy quite a long time ago, about 1790s, who was called Count Rumford. Now, he wasn't a count originally, but he fought in the American Revolutionary War. And he was a lieutenant colonel there, and I think he got knighted. And then later on, he rushed off to Bavaria and joined their army and worked in that area. And he became a count, so he goes under the rather cool name of Count Rumford. Now, if you think about it, he was working in a military situation, and he was using cannon a lot. So that was the kind of large gun that he had. And making cannon was quite an interesting job. Sometimes if you look on maps, and we've got some near us in Telford, we've got places that go under the name of boring mill, which I think is rather a cool name. And a boring mill is where they took a chunk of cannon material, sort of bronzy material, and they took a big drill and they slowly but surely drilled into the cannon and made a hole down the centre, which was the bit they were going to put the cannonball in. Now, that wasn't a particularly easy task. And one of the ways you could do this is you could do it with horses, and you put the horses on a gin, where the name sort of engine comes from. And those of you who know about horses, it's sort of a horse walker. So they went round and round in circles, and some gears turned, and those gears turned a drill, and slowly but surely that drill worked its way into the block of metal and drilled out the centre, the bore of the cannon. Now, I always tell this story as Count Rumford thinking about this, because he noticed that when you drilled into the metal, it got really hot. And he thought, that's really weird. Where's this heat coming from? Because there are no fires or matches or anything. All I'm doing is just turning a drill, and the cannon's getting hot whilst I'm drilling into it. I know you guys know about friction now and things like that. But here's the bit of the story that I kind of twist around a bit. So you've got to make a cannon. So you get your cannon set up and you get the drill. And you can either attach it to a water wheel, or you can attach it to your horses in their gin. And the horses are going round and round and round, and they drill into the cannon, and the drill goes further in, and the cannon gets hot. And the horses get a little bit tired. So the drill goes slower, and it bores into the cannon more slowly, and the cannon doesn't get as hot. But what you do is you feed the horses with grass and hay, etc., and after a rest, they get up and running again, and they go round and around the horse walker, the gin, rapidly, and they bore into the cannon. The whole process speeds up, and the cannon gets hotter again. Well, you might think that's pretty obvious, but just think about what happened there to make the horses get going again and to drill better and make the cannon hotter. The strangest thing happened. You fed them some grass. And if you fed them some grass or some hay, which had been growing in sunlight, they could move faster, turn the drill faster, bore the cannon faster, and as it was drilling, the cannon got hotter. Now, again, you're probably saying, so what? But just think about it. The sun shone down on the grass. So the sun must have given the grass something. The grass then went into the horses, and they ate it, and it gave them something. It was food. They were then able to walk much more quickly. The cannon was made more quickly, and as the drill went in, the cannon got hotter more quickly. So if you can follow the logic of that, and I think that's what Count Rumford was doing about 1798, that sort of period, he was seeing that there was some kind of flow going through the system. And this is the energy flowing through the system to make the cannon. So just to summarise, isn't it interesting that the energy to make a cannon hot came from the sun? So the sun produced light and heat. That then made the plants grow via photosynthesis. The horses then ate the plants. They then used that energy to move faster, and that speed that they developed, that kinetic energy, then bored the cannon and made the cannon hot whilst there was some friction and rubbing. So one of the main sources of energy for all of the food that we get, and if you think about it, that's you running around and playing sport, where you got that energy from originally was from what you ate, and where that got its energy from, would you believe it, was from growing under the sun. The sun seems to be a major source of energy for living things on Earth. So, have you ever thought about that before? It's really strange, isn't it? That when you run around and play netball and cricket and rugby, etc., you got your energy originally from the sun. So if you're a vegetarian, you ate plants that got their energy to grow from the sunlight. And if you eat meat, the animals got their energy originally from eating grass, etc., that also got its energy from the sun to grow. And it used the process of photosynthesis to turn that energy from the sun into chemical energy in the plants. So there we've got one energy resource. And I'd like you to think that that energy resource is energy from the sun initially. But what about all the electrical items and things that are moving around in your house that haven't eaten breakfast this morning? Things like the washing machine and your phone that's plugged in and your laptop that's working and the TV. They must be getting their energy from a different place. So what I'd like to look at next, and I'm going to go up to the board to do that, is the energy resources to power electrical devices. Okay, so now let's have a look at some energy resources that are slightly different from the food that we eat that got its energy from the sun via photosynthesis. When we plug things in at home and we use the sockets on the wall and the mains plugs, we're getting our energy from a power station. And I wanted to look at the different types of energy that are fed into power stations and how those affect the environment and how long they're going to last for. So it's quite a long list, but it's not too difficult. You can use some of these energy forms straight away. So the one I'm going to kick off with is coal. So coal, dug up from the ground. We live in an area in Telford where it was a major coal mining area. And that coal, sort of draw some lumps of coal, that coal can be burnt directly. Now, in a power station, you obviously get vast amounts of coal brought in by train. And that coal will then be burnt. It will boil water, produce steam. That steam will turn turbines, which will turn generators, and then we get electricity coming to us over those high pylon wires over the national grid. So when you plug in at home, some of the energy that you're using to drive things like washing machines and charge your phone may well have come from coal. Our cars driving around, unless they're direct electrical cars, oil. So a power station can use oil as well as a source of energy and can burn that oil and go through the same process of producing steam and that steam turning turbines and generators to make electricity. I've got a car that actually runs, a Land Rover that runs on gas. So, not quite what I'm drawing here, but a little sort of gas bottle. And gas, again, can be burnt directly and in a power station can be used again to boil water and to drive those turbines that turn the generators to make electricity. Now, let's just have a closer look at those three, because they're quite important. Okay, these three go under a particular name, and it's a name you need to know. These are called fossil fuels. So these fossil fuels were laid down under the sea and under the ground millions of years ago. Coal was a sort of series of plants that died in boggy ground and in marshy areas, and layers built up, and over millions of years of being there under pressure, that kind of rotted away and turned into coal. Oil was more under the sea, microorganisms and other organisms, when they died, falling to the seabed and again layering up, getting crushed, and over millions and millions of years, that sort of sludge turned into oil and gas. So just have a listen to what I've said about that. These were produced millions of years ago. Okay, so they're not being produced rapidly now. So we're using coal, oil and gas that was laid down and formed over millions of years. And when we've used these up, there won't be any more being made. Partly because the process is so very, very slow, and also the earth has changed. So these go under a very particular name. These three fuels are called non-renewable. And I've separated those two words just to make it a bit clearer. Now, just hear that again, okay? These, because they are not being replaced as rapidly as they're being used, are called non-renewable. They're not being made. They're not being renewed. I don't like teaching bad physics, but that doesn't say non-reusable. Okay? When you've kind of used a form of energy, that's it. You've turned it into another form. So no forms of energy are sort of directly reusable. Okay? You might say, oh, well, what about a rechargeable battery? Well, you use up the energy in the battery to do something, and then you have to get some more from somewhere else to charge it back up again. Okay? So, three forms of energy there that we use a lot, particularly in power stations. Because they were laid down millions of years ago, we call them fossil fuels, and because they will run out in the foreseeable future, they're described as non-renewable. So these are terms you need to know. Obviously, when we burn these, we get carbon dioxide and other materials coming out of them, and the carbon dioxide is not good because it's a greenhouse gas. We also get acidic gases as well that cause acid rain, and the sheer act of getting these out of the ground can also be damaging and polluting for the environment. So we're trying to reduce our reliance on these, partly for environmental reasons, and particularly because they will run out because they're non-renewable. So let's have a look at some other forms of energy that we can use, particularly to provide electricity or to heat our homes. And there's a whole list of these, but we'll start off with one I'm sure you're quite familiar with: solar energy. So solar energy, you get the solar panels on the roof of your house, and that energy comes directly from the sun and can be turned directly into electricity. I'm sure you've all seen wind turbines. Okay, I'll sort of draw a little propeller here. There we go. Wind turbines. I'm being really careful here to sort of not call it wind energy. I know that's what it's known as, but it's really kinetic. It's moving air that turns the blades on the turbines. And we're seeing more and more of these in the UK. One that really hasn't been fully developed yet is wave energy. So you've seen surfers on the beach being dragged along at high speed and given energy, given kinetic energy. And if we could harness that wave energy, especially in the UK, it would be absolutely wonderful. We could use that to, like solar and like wind, to make electricity directly to power our houses. There's another one that we do have in the UK, though you may not have seen it, and that's hydroelectric power, HEP, hydroelectric power. It's actually a little bit simpler than the name sounds. You basically have a dam, and at the top of the dam you have some water that's blocked off, and it flows down the hillside through pipes, and as it flows down it turns turbines which turn generators, and so you get a lake at the top of the hill losing its gravitational potential energy and flowing down to a lower lake, and that produces electricity. We have one near us in Wales that actually produces electricity when it's needed during the daytime, and then rather strangely at night time when the power stations elsewhere are running, it uses that spare electricity to actually pump the water back up again so it's ready to go if it's needed. It can be turned on very rapidly if there's a demand for electricity. Another one that we used a lot at home when I was a kid was biomass. Again, sort of complicated name, but basically stuff that's been growing like trees and things. So there's a range of these. You can take pieces of wood and put them straight onto a furnace or a fire and use that to heat your house, or you can use it to produce steam in a power station. They sometimes take pellets of recycled wood and feed that into the boilers of power stations where coal would have gone to generate electricity. And they can grow with scanthus, it's elephant grass, big tall grass, and use that to burn to produce electricity as well. There's another one that I don't think we have in the UK, but they have in France, and that's tidal energy. Not quite sure what sort of diagram I draw for that. But what they do there is they take, sort of viewed from above, they take an estuary going out to sea, and they block it off with a dam. And when it's low tide, the river water coming through the dam turns turbines and generates electricity. And then they block it off, and then when it's high tide, the water flows back up. You can see this happening near Bristol, where you go over the motorway bridge over the Avon on the M5, and you can see sometimes the river level really low when it's low tide and really high when it's high tide. But they never built a tidal power station there, but who knows what will happen in the future. Now, these ones are quite interesting because clearly they're not fossil fuels. They haven't formed under the earth over long periods of time. Okay, but do you remember Count Rumford and me going back to saying where does the energy originally come from? And I was suggesting it came from the sun. Solar energy from the sun. Wind energy caused by the ground heating up due to the sun and creating convection currents and wind. Wave energy is caused by wind actually blowing over the sea and creating waves. Hydroelectric, caused by the sun heating up water and causing it to go up into the atmosphere and then rain down on the high mountains, producing a lake. Biomass, we know about that one. That's light from the sun causing photosynthesis and things to grow. Tidal, a little bit more complicated. That's more caused by the gravity of the moon actually kind of causing a bulge of water as the Earth rotates during the day. But we haven't fully harnessed these, but look carefully. On all of these, apart from biomass, nothing is burning. So none of these, apart from biomass, produce CO2 or any nasty gases. And that's really, really good news for the environment. You might wonder about biomass. Well, if you replant the trees, then the carbon dioxide that you put into the atmosphere will be removed again, or at least you're replacing it by regrowing and then burning that and then regrowing it and burning that. So the trees that are growing are taking carbon dioxide out of the atmosphere that's then going to be put back in, a sort of almost one-to-one process. So these can be seen as being environmentally better. Just before I say they're much better environmentally than anything else, solar panels, some people don't like them on pristine farming land. Wind, they don't like the sight of the wind turbines and the energy that was used to put them up on mountains. People don't want the coast surrounded by wave-powered devices. Lots of people, quite understandably, don't want to flood valleys in pretty mountainous areas to make lakes for hydroelectric. Biomass is not quite so contentious, but we mustn't cut down rainforests and places to produce energy from burning wood and then not replace it. That would be madness. And tidal has a whole series of issues. One of the main ones was affecting aquatic life and birds and things if you affect the tidal flow through a river. But these are not fossil fuels. But the great news is that the sun's going to keep shining. These are never going to run out, so they are renewable. Remember, renewable doesn't mean reusable. Renewable means they will never run out in the foreseeable future, so perhaps these are the ones we should be working towards producing more of. So there's one really contentious one I've left off the list, and we'll add that to the bottom, and that's nuclear. Nuclear energy. The symbol looks like a propeller, but in fact what it represents is radioactive material giving out rays. Okay, so nuclear energy is complicated, but this is the energy in an atom. It's a very difficult thing to demonstrate in a classroom, but in an uncontrolled way, a nuclear explosion. You might have seen mushroom clouds and things like that. Okay, that's where energy inside the atom is given out. And what we do in a nuclear power station is we don't blow stuff up, obviously. We release energy from atoms slowly over a period of 10, 15 years, and we have to add more nuclear fuel into the nuclear power station. But what's really clever is when the atoms split via a nuclear reaction, they give out their energy as heat, and that energy can be immediately used to boil water, produce steam, turn turbines and drive generators and produce electricity. So there's no burning with nuclear. Whether it's renewable or not is questionable, and we go through phases of yes it is, no it isn't. Okay, but there is good science to suggest that we could produce nuclear energy in a form where we wouldn't run out of it in the foreseeable future. Environmentally good or bad? That's a very tricky question, and you have to make up your own mind there. I've gone through being pro to anti to pro. I'm all over the place with nuclear energy. But nuclear energy does produce nuclear waste. And that nuclear waste is very, very, very toxic, and it remains around for thousands, if not millions of years. So the waste we produce from nuclear power stations will be the responsibility of generations beyond anything that we can imagine. And many people suggest that isn't a good thing. But what's interesting is something called energy density. That if you want to build a power station out of wind stations, you have to put a lot of them on the hillside. You have to put a lot of solar panels up. Coal has a large amount of energy bound into it, into a small amount. Oil has a large amount of energy in it, and so does gas for its volume. And nuclear energy is incredible. For its volume, it's about 1 million times more packed full of energy. So the amount of nuclear waste and nuclear fuel needed is actually very, very small indeed. It's hundreds of thousands of tons of coal for the, maybe millions of tons of coal for the lifetime of a coal-fired power station. And a nuclear powered station only uses a few hundred tons of nuclear fuel in its whole lifetime. That might be 30 or 35 years. So nuclear power has got a lot going for it, but of course you do have to mine some of the nuclear materials, the uranium. There are risks about what would happen if terrorists got hold of that material. And of course, there are all the issues with what do we do with the nuclear waste. But that's set against the fact that this produces vast amounts of energy for a very small amount of material going in. So I'm not going to say whether it's renewable or not. I tend to think at the moment, from what I've read, that it is. But let's just summarise. So to turn the lights on in our house, to charge our phones, etc., we need to get energy in the form of electrical energy. That can come from different power stations, and here are the types of power station we could have, the type of energy input they could have, and I'd like you to think about the names of them, which are fossil fuels and which aren't fossil fuels, and which are non-renewable, will run out in the future, and ones that are renewable and won't run out in the foreseeable future. So, quite a difficult and long video there. I think you need to perhaps go back and pause and look over a few bits. But I hope you now feel you've got a better understanding of the energy resources we use to make electricity.